All right, let's dive right in. Today, we're going to peel back the curtain on how modern AI actually gets built. We're going to break down how even the most ridiculously complex models are put together using the deep learning frameworks we have today. Let's get to it.
You ever look at a model like ResNet 152 with its, hundreds and hundreds of layers and just think, how on earth do you even begin to build something like that? It looks impossible, right? But the secret is, it all starts with one surprisingly simple idea.
So first up, let's talk about the fundamental parts. To build these massive models, we need something way more powerful than just a single layer. We need a kind of universal building block.
And that simple idea is the module. The module is the core concept that makes all of this manageable. Seriously, just think of it like a Lego brick. It could be a simple little piece that's like a single layer, or it could be a whole pre-assembled component, like an engine block, which represents a whole bunch of layers working together. This reusability is the absolute key to building huge networks without losing your mind.
Now, the simplest way to use these modules is to just line them up in what's called a sequential module. It's basically an assembly line. Your data goes in one end, gets processed by the first station, then gets passed to the next, and so on until the final product pops out the other side. It's a really clean, really powerful way to build a ton of common models.
Okay, so we've put our machine together. Now let's pop the hood and look at the thousands, or hey, even billions, of tiny little knobs that let it learn. We're talking about managing the model's parameters.
There are really two main things we need to be able to do with these parameters. First, we've got to be able to access them, to peek inside a specific layer and see what its weights and biases look like. That's super important for debugging. And second, and this is a really cool trick, we need to be able to share parameters between different parts of our model.
So by default, every layer you create is its own separate thing. It's got its own unique set of weights and biases. When the model trains, these two sets of knobs get turned completely independently of each other.
But what if we want two layers to act as perfect twins? Well, we can use something called tied parameters, and this is where it gets really interesting. The two layers aren't just similar, they are physically pointing to the exact same numbers in memory. That means if you update a weight in one layer, the other one changes instantly because they are literally the same object. It's a fantastic way to enforce some kind of symmetry or to seriously cut down on the number of parameters your model has to learn.
Now, before a single piece of data ever touches our model, before any learning can happen, we have to set all those parameter knobs to some kind of starting value. This first step, called initialization, is absolutely critical. It can make or break your training. Deep learning frameworks come with a whole toolbox of different ways to get this done. You can use something simple like a normal distribution, or even just set everything to a constant value. But smarter methods like Xavier, which is also called Glorit initialization, are often the default because they look at the size of your layers and pick starting values that help prevent your signals from either exploding or just fading away to nothing. The big takeaway here is the starting point matters a lot.
Okay, so here's a neat little problem that comes up all the time. When we define a layer, we definitely know how many outputs we want, let's say 256, but we might not know exactly how many input features our data will have. Will it be 20, 50? Who knows? So the framework just leaves a little placeholder, a question mark, in the shape of the weight matrix.
And then, the moment of truth. The very first batch of data starts to flow through the network. The framework sees it and goes, aha! So the input has 20 features. Got it.
And here's the magic trick. It's called lazy initialization. The framework automatically fills in that question mark, creates the weights with the perfect shape, and then does the initialization. This one little feature saves developers from the absolute nightmare of manually tracking input shapes through super complex models. It's a game changer.
So far, we've just been using the standard Lego bricks that come in the box. But what happens when the piece you need just doesn't exist? Well, that's where the true power of these modern frameworks shines. They let you design and build your very own custom layers.
Building a custom layer puts you in the driver's seat. Your job is actually pretty simple. You tell it what parameters it needs, you write the code for its unique logic, and you make sure it takes an input and produces an output. But here's the best part. You only have to define how data flows forward. All the complicated calculus, the backward propagation, the gradient updates that make learning possible, the framework handles all of that for you, automatically. This is what lets researchers experiment with wild new ideas and push the entire field forward.
Okay, we've built it, we've trained our masterpiece. The final steps are to save our work so we can use it later, and of course, make sure it runs as fast as humanly possible.
Now, this is a really common point of confusion, so listen up. When you save a model, you are almost always just saving the parameters, the learned weights and biases. You are not saving the Python code, the actual architecture. To bring a model back to life, you have to first rebuild that architecture in your code, creating an empty shell, and then you load your saved parameter values into it.
Now let's talk about speed. The absolute explosion in AI over the last decade is pretty much entirely thanks to one specific piece of hardware. So why are GPUs so essential for all of this?
Well, GPUs are masters of doing many things at once. All those thousands of simple matrix multiplications that deep learning relies on, a GPU can do them all in parallel, at the same time. This is what turns a training job that would take weeks on a regular CPU into something that takes just a few hours. They are the high-performance engines of modern AI. But of course, there's a catch.
And this is the critical bottleneck you always have to think about. The math on the GPU is lightning fast, but getting the data to the GPU and back from it is incredibly slow in comparison. Every time you move data between your computer's main memory and the GPU's memory, you're slamming on the brakes. The key to high-performance code is to keep as much data on the GPU as possible and minimize those transfers.
So, there you have it. We've gone from the basic Lego brick of a module, through managing parameters, initialization, and finally to saving our model and running it on super fast hardware. You now have the fundamental blueprint for how modern AI is constructed. Which really just leaves one question: what problem would you solve?